Hey everyone, how's it going? My name is Mitch Carswell. I'm a project ergonomist working for Sandalwood Engineering and Ergonomics based out of Livonia, Michigan. And welcome to my presentation on an applied review of multi-person lifting. All right, so getting right into it. What exactly is multi-person lifting? Well, very simply put, it's two or more individuals that are lifting the same object. It's synonymous with team lifting, and I might use those two terms interchangeably throughout the presentation. But the focus of this presentation will be on how we can assess team lifting appropriately and what impacts these have on ergonomics in the workplace. At the end of the day, the goal of any ergonomic program is to identify risk and analyze it using validated assessment tools such as our NIOSH lifting equation, digital human modeling if that's available to you, as well as any other tools in your toolbox that can assess lifting. And then what we'd like to do with those results is develop solutions that really protect our workers and follow the hierarchy of controls, which will be outlined on the next slide. So what exactly is the hierarchy of controls? It's this inverted pyramid that you can see on the right-hand side of the screen, and it's basically a workflow. So at the top, we have elimination, which is always the ultimate goal at removing a hazard from a work area, but however, it's not always possible. Moving down the pyramid, we could see other options such as substitution and engineering controls. This is where we would start to see items such as lift assist and lift aids being added to a workstation for workers to be able to use and alleviate some of the stresses and strains from lifting. However, those can sometimes be expensive, hard to implement, and not always possible either. So where does team lifting really fit in on this current hierarchy of controls? Well, that would be right here under administrative controls. It's changing how the work is done. We're not able to necessarily eliminate it. We've looked into trying to substitute out lighter weight parts. We've looked into implementing a lift assist, and none of those options were necessarily feasible for the designated work site. So now we're stuck with controlling how the operators do the work, either through training or work instructions. So what are some of the risks associated with multi-person lifting? Well, one, innately, whenever we have two or more individuals lifting an object, it tends to be large, it tends to be heavy, it tends to take more than one person to be able to handle this load. The second part of that, with objects that are larger, especially as you can see in the example below, we have a large cylindrical object that would definitely require two individuals. And what we can see is in the second picture that the center of gravity is actually effectively changed from where it would be, and the distribution of the weight between the two operators can change. And the third element of risk that we've really highlighted here is that it requires really effective communication between the two operators completing a lift. When we have two operators lifting together, we want to make sure that they're in sync. They're lifting at the same time, and this could be a lot more challenging given the noise of general work areas, especially if we're in areas with heavy machinery, other workers, high-lows traveling around. There starts to be a lot more factors that can impact how two individuals communicate with one another. So the first step, as all of us know, is trying to gather as much information as possible. When you do have a problem, you want to understand that problem as much as you can. So we started with a literature review that looked at 25 published articles, 12 of which were found to be relevant for the information that we were looking at. We used the following keywords such as team lifting, paired lifting, manual material handling. As well, we surveyed 13 various organizations across multiple industries on their guidelines, standards, assessment methods, and what they're doing for team lifting in the workplace. As we were doing our literature review, one of the papers that stuck out to us the most was this one that was completed by the United States Department of Defense. They actually developed this table that is shown below, which shows maximum design weights for acceptable team lifting. It's focused on the destination of the lift, as well as the anthropometries that are going to be completing the lift. On this first line, we could see that if we were going to be lifting an object from the floor and placing it to a destination of 152 centimeters or 5 feet above the floor, the max acceptable lift for a male and female team would be 14 kilograms or 31 pounds. Conversely, for males only, it would be 21.9 kilograms or 48 pounds. The interesting part of this study actually moved on and evaluated for frequency, which we'll go over the correction factor on the next slide. But for now, I want to focus in on how they evaluated for different box depths. You can see that we have 4 different boxes across the bottom, each of which have an 18 by an 18 inch front and vary in box depth. So the first green box, we have a 12-inch depth, and this would result in no correction factor. When we start to exceed a box depth of 12 inches, but does not exceed 36 inches, so anywhere in between these two box sizes, we would decrease the force or the max acceptable weight by 33%. As we go over 36 inches, we would decrease by 50%, and anything over or greater than 48 inches in box depth, we would decrease by 66%. As mentioned previously, there was also a frequency correction factor that was developed, and this is based on the fact that the original table was developed with a lift assumed to be less than once every 5 minutes or a total of less than 20 per 8-hour shift. So we could see this formula below where you would input your number of lifts per minute, multiply it by 8.33, divide by 100, subtract that from 1, and then actually multiply that by the limit from the table to determine what that max acceptable lift would be in a cyclic application. This could be used in concurrence with the actual box dimension correction factor, so you could be applying more than one if that is best suited for the assessment purposes. But with this information, we are able to correct for frequency and box depth. Continuing on, we were able to take 4 of the other studies that were identified from our literature review and place them into this table, outlining the team lifting capacity expressed as a percentage of the summed individual lifting capacity. So what this is effectively showing is if we have 2 people or 3 people or even 4 people lifting the same object based on their movement style, so isotonic, isometric, or isokinetic, you sum those individuals up, and then you would take a percentage, and that would be your lifting capability. To go into this further, we have isotonic, which would be the similar motion of a bicep curl, so where the muscle actually contracts and a load is moved through a motion. We have isometric, which would be very similar to a plank, so the muscle's contracting, but there is actually no movement. And then we have isokinetic, where we're moving with a controlled speed and moving a force throughout a range of motion. So for our purposes, this is what we were effectively looking at, this isokinetic movement. Stepping away from the literature review, we get into some of the industry benchmarking. So this is actually us reaching out to a variety of different companies and organizations for their practices. We could see that there are various different practices. We have 60% of the load per person as an assessment methods. We have multiple companies with no team lifts. So a few of these, we have individuals who are working in isolation or unable to have another party come over and assist them lift anything. Some which have actually taken that elimination route and designed their work that would be required to be done by team lifting and had it done by automation. We can actually also see a few different companies who set out just general lifting guidelines based between certain weights. So based on what we heard back from the industries, we could see that this was heavily manufacturing focused, with over 50% of our responses coming from the manufacturing sector. We also have services in mining, delivery services, essential services, food processing suppliers, and 3 that chose to remain anonymous. Looking at the actual assessment strategies of some of these businesses, we could see that almost 50% of them are not permitting team lifting. So whether they have completely eliminated it from their process, we have work that doesn't require it, they're not lifting heavy objects, and some that just don't have an assessment method as well. But we can see here that in the second line, the most commonly used assessment method or practice at these organizations is to ensure that each of the operators completing the lift are capable of handling 60% of the load. We have one that recommends 50% of the load, so just a straight lift. So just take the sum of the two individuals and their lifting capacity would be permitted. And then, as mentioned previously, we have two different companies that just have ranges. Originally, we have a 40 to 80 pound range, and then as well, this other company was 35 to 48 pounds, and we can notice that it's asterisked. This is because if operators choose to lift more than 48 pounds in a team setting, they are permitted to. They understand the risk, and one that chose to remain anonymous. So now that we better understand what everybody is doing and what some of the approaches are through academia, we can start to move forward. There wasn't too many consistencies that were found. The biggest consistency was a lot of companies have moved towards elimination, which is great. But those that are not still vary in their assessment methods. We could use a generic guidelines, such as what the U.S. Department of Defense has developed, and limit team lifts to 85 pounds, 44 pounds if they're lifting to greater than 36 inches, and 60 and 31 pounds if lifting to greater than 5 feet. So taking what we've learned based off our industry surveys and reading through the literature and understanding the motion patterns, we have devised that the most consistent approach and the best practice would be to assess and ensure each individual is capable of supporting 60% of the object's weight when lifting in pairs. To determine the individual's strength capability, using a static strength assessment such as a NIOSH lifting equation, jack study, 3D SSPP would be used to identify that. So taking what we just went through on the previous slide, I think it's a great time to go through an example. So over on the right, we have two individuals. They're going to be lifting this wonderful 70-pound box, a little heavy for my preference. And they're going to be starting at a vertical of 18 inches from the ground, horizontal of 10 inches, and they're going to actually be lifting this box up to 75 to 45 inches, sorry about that, and a horizontal of 10 inches. So still good horizontals, but still working through a good range of heights here. You can see it's just a plain cardboard box, so there's no discrete handles or gripping points for these operators. And let's assume that they'll be doing this together once every half hour for a full shift. So the first step in assessing would be to determine what is the 60% of the actual load. So what is one operator going to be required to handle? To do this, it's very straightforward. Multiply the load, so this 70 pounds by 60% or 0.6. And then we get a load weight of 42 pounds. So this is what we would be expecting each operator to handle, assuming some postural stresses and some considerations for lifting in a team as opposed to lifting individually. We go ahead, we input this into our NIOSH lifting equation. This is a free calculator that's online. I believe it's from the University of North Carolina State on their website. So if you give it a quick Google, easy to pull up, and the best part is it's free to use. So using that, we input the remaining number of our inputs, and then we calculate our recommended weight limit as well as our lifting index. So we could see, given this example, we have a lifting index for each operator, assuming that they will be executing the same lift. They would each have a lifting index of 1.37. Now your company will have their own guidelines about cut points, but from the industries and the clients that I've worked with, this would be deemed acceptable. So now that we've gone through and we've assessed whether or not a lift was acceptable, how do we go through and assess or set a force target based on the postures that we're lifting? So going through, we use the same NIOSH inputs and calculator as beforehand. However, we left the load weight blank. We are then able to obtain our recommended weight limit of 30.7 pounds. Now, in this scenario, we would multiply it by our acceptable lifting index, and I've chosen to use 1.5. So when you multiply that out, you get a number approximately 45 pounds. And then divide that number by the 0.6 to determine what would be the total supported weight of each for the team to lift. So in this scenario, we have a max acceptable load of 76.75 pounds. Something that's important to hear, we are assuming that both operators are lifting with the same posture. So if you have two operators and they're going to be lifting from different areas, what the recommendation is you take the operator that has the lowest recommended weight limit or the least strength capability and use that number as what to determine your max acceptable load or even assess your strength target. Now, how does this change when we're lifting with more than 2 people? So we understand that the same assessment method would still apply, where each person would be evaluated individually for their lifting capacity. The max acceptable lift would then be totaled, so you have person A plus person B plus person C for their total weight, and then the theoretical lifting capacity would be multiplied by that same correction factor of 60% or 0.6 to determine a max acceptable lifting capacity for the team. And in the bottom, we can see we have a recommended weight limit of each person, so 1, 2, 3, and 4, and we would be able to identify what the team total of lift would be. So given a 2-person lift, we have a 66.7 pound lift that would be acceptable for this team. When we add a person, we see that a 72 pound is actually acceptable. And then when we have a 4th person, 96 pounds would be acceptable. So as some of you may have noticed on the previous slide, when we were looking at lifting capacities in teams, there was not a significant increase between lifting in 2 people and lifting with a 3-person team. And this is because adding more people to a lift doesn't necessarily eliminate the risk or decrease it significantly, and it can actually introduce multiple different sources of risk. With an additional person, there's more coordination that's required, as well as more points of failure. So something that would be very important if you're going to have lifting or team lifting as a part of your everyday and just in the workplace, have training specific to lifting in pairs or teams to reduce the variance between lifting habits. It's something that we already have, I think, for the most part, is proper material handling training and how to lift, whether it's a poster or something like that. If you're going to be doing team lifts, really having that deep dive or that specific training on lifting in pairs. In that training, there should really be a focus on the teams lifting in a similar manner and lifting in synchronicity. And for this, the communication portion is key. How many of us have said, okay, lift on 3, and then somebody says 1, 2, 3, lift? Well, those are 2 completely different sayings, and what that could actually lead to is one person beginning a lift a half second before someone else and supporting a greater portion of the weight and increasing their risk of injury. And so when we have 2 people that are planning to lift together, it's also critical that we try and match their statures. So having people of equal heights and making sure they're on the same page when we lift can go a long way to preventing those discrepancies in the weight distribution of the object. Something else that is not on this page but is also very important is planning your route for your team lift, making sure that the pathway is clear. Those I think are very similar to just lifting in general and just good workplace hygiene, but even more so important when we have 2 people carrying the same object, as one person could be walking backwards and they might not necessarily be able to see any objects or hazards in front of them. So to wrap up, what are some of the really key takeaways here? The key takeaways for us were there are no current standard methods for assessing multi-person lifting. We're working to establish a best practice and we're learning every day. There's a lot of additional strains and stresses when you're lifting with someone else. A lot more understanding and coordination needs to go into the actual lift. And what that effectively does is when you have person A that's capable of lifting 50 pounds and person B that's capable of lifting 40 pounds, you're not necessarily going to be able to lift 90 pounds without failure. There's a lot of other considerations that need to be taken into account when lifting into teams. Yep, so I'd just like to say thank you to everyone. Looking forward to the discussion session after. If there's any questions, let me know. And it's just a special thank you to Sarah Spiker, who was instrumental in putting together the literature review for this, a coworker of mine, as well as Allison Stevens, Rob Fox, and Jack Liu over at NIOSH. They all provided great insight when we were devising this and going through a lot of the literature and reaching out to companies on their assessment methods and just understanding all that there is to understand with team lifting. I know it's something that we try not to have in in our workplace, but it's just a gap in our current knowledge, and we're just trying to better understand it. So thank you again.